How to add and use compressor curves in AspenHYSYS. There are 4 operating modes that representing compressor types in the software. The first one and the most common one, especially for the large production facilities, is centrifugal compressor. The options for curve input in AspenHYSYS for this type of compressor is single molecular weight, which is the subject of this session, multiple molecular weight, which is suitable when molecular variation is significant, multiple IGV, non-dimensional, and quasi-dimensionless. This type of curve input we will not discuss in this session, but in the future, we will give an example to see how you can add them. In addition, in the next slide, we will go through the effect of molecular weight on the compressor curve. The next operating mode or compressor type in AspenHYSYS is reciprocating one. The other one, screw compressor, and wet gas, which is a specialized compressor and is used for multi-phase system. Effects of molecular weight on compressor curve, which is very important topic. Here you can see 2 plots for fixed speed compressor, which is a single curve, and they are based on head versus inlet actual volumetric flow and head versus inlet mass flow. You can see higher molecular weight shift the curve to the right when plotted in actual volumetric flow basis. You can see it clearly here. The dark blue one is lower molecular weight, and the orange one is higher molecular weight. So the curve, when the molecular weight increase, is shifted to the right. But when it's plotted against the mass flow, then the shift is very small, and actually in the stonewall region, it can be shifted to the left. So it's the way you implement the curves. In AspenHYSYS, you don't input the curve and in mass flow basis. So what is important is this curve. The next one is higher molecular weight increases the actual volumetric surge flow. So you can see clearly here how the surge flow is changed when the molecular weight is increased. And this is very critical in the surge control system. And the highest molecular weight case should be considered for surge flow when it is in actual volumetric flow basis. Higher molecular weight leads to a slightly higher head at the given volumetric flow rate. So you can see it here. For example, in this volumetric flow rate, the higher molecular weight case will give higher head. So you can see it from various equations. And this is a logical result. In addition, there are something in when analyzing the compressor performance. There is one analyze based on having a curve and changing the parameters and see how the performance changes based on the given curve. The other one is how the curve itself changing based on specific conditions like molecular weight, which is related to the composition itself. And this change in the inherent performance curve of the compressors can typically be analyzed with Buckingham P similarity or Buckingham P theory. So there you can have the non-dimensional numbers like flow coefficient, head coefficient, Mach number, and some other like Reynolds number. And based on that, these non-dimensional numbers, you can scale up the curves when the inlet condition is changing. I may have a session for introducing the Buckingham P theory for the compressors and pumps and maybe other equipments. Higher molecular weight also leads to a more rapid fall of the curve and the stonewall region. This is visible in both plots when plotted against the actual volumetric flow and also mass flow rate. So you can see here clearly for high molecular weight in the stonewall region, the reduction in head is too quick. Effect of molecular weight on the compressor curve when it is variable speed. So it's similar to a single curve, but in variable speed we have infinite speeds. So you can see how is the effect. The effect is more visible when it is plotted in actual emitted flow, and you can see clearly the curve is shifted to the right. But for the mass flow, the difference is not that visible, but still you can see that the surge line is have a similar trend. So when we are plotting for both surge for both actual emitted flow and mass flow rate, the higher molecular weight case should be the base for surge control. Effect of suction pressure on the compressor curve. For a fixed speed compressor, which is a single curve as mentioned before, if you use the curve in mass flow rate basis, you need to use different curves for different suction pressure. You can see it clearly here from this plot, which is head versus inlet mass flow. You can see when with higher suction pressure, the curve will be shifted to the right, and also the surge point, as well as the so on. But when it is plotted against actual volumetric flow rate, the difference in the curves is negligible. So you can still use a single curve, which is for a specific molecular weight for a range of suction pressure. So the difference is small. And this is the case also for Aspen HYSYS. So the effect you can see in variable compressor. So you can see how visible is the change when the suction pressure increased and the plot is in mass flow rate basis. But with actual emitted flow, the change of operating window of the compressor is very small. Our received compressor curve, hypothetical compressor curve from a vendor. You remember in the last session, we made the process data sheet, and on that process data sheet, since we had a very small variation in the molecular weight, we didn't consider that. So, and we wanted to receive the curves in volumetric flow basis and implementing in Aspen HYSYS. So for our case, one curve will be enough and covering all of the operating conditions. So here I plotted four speed curves, four curves in different speeds. But in theory, we have infinite number of speeds between the minimum and maximum speed. This is the curve data just for illustration. I have it also in the Excel sheet. Later you see when I implement it in the simulation. Here, just before starting the simulation, in some screenshot, I will show you how to add the curves, and later we will also repeat it in the simulation itself. So in the design tab and parameter subtab, the first thing is you have to remove the efficiency which you put it before, because if you keep it there, you will get an error because we will have a violation of degree of freedom. So it will be more input than is required, because the efficiency will be calculated based on the curve. Then selecting the operating mode or compressor type, and then the curve input option, which is in our case single molecular weight. So now adding the curve data in the compressor itself, so you need to go to the rating tab and curve subtab. The first thing, as you may know, the majority of compressor curves are based on polytropic efficiency, so we have to shift it to polytropic efficiency as the basis. And then adding a curve, so it will be a window open. You can add the name of this. Typically, it's better to add the speed, for example, 7,000 RPM, 8,000 RPM, and also the speed itself. And also remember to select the units according to the data you have. When you added the curves, Then you can activate them, enable the curves, and based on the way you want to solve and the study you want to do for the compressor, either giving the speed or manipulating the speed, or giving the discharge pressure. So if you give the discharge pressure, then the speed will be found. Let's go for the simulation. Let's assume these curves are based on our process datasheet for the compressor, and we received it from the vendor. Let's implement them in the simulation. As mentioned in the slide, the first thing is to go to the Design tab and Parameter sub-tab and removing the efficiency, because it will be predicted from the curve. Then we need to select the operating mode or compressor type. Here for our case is centrifugal. And also the curve input option. In this case, we had negligible variation in molecular weight, so we had a single set of curve, because these curves are at different speed. If we had a significant variation in molecular weight, we would have several sets of curves at various speeds. Then we go to the Rating tab and the Curve sub-tab and choosing the polytropic efficiency. Typically, we receive the curves based on polytropic efficiency for the compressors, not adiabatic. Then clicking on the Add Curve. So adding the curves one by one. So I'm starting from the minimum speed. So then the minimum speed is 7,000 RPM. The flow rate unit is actual cubic meter per hour. And the head is kilojoule per kilogram. So now I copy the data I have in Excel sheet and paste it here. So now it's done, only also the speed itself. Then add in the next one. The next one, 8,500 RPM. And also remember to make the unit. You could also make the unit in the unit set to have it kilojoule per kilogram as a default one. So this one is also done. Remember, always check the units. So I added the curves. Now they are ready. So before everything, I need to activate them. So also plotting the curve also. After activation of the curves, I need to enable the curves for the simulation. If I enable, since I have already a discharge pressure given in the simulation, the compressor speed will be calculated for us. So I will not have any compressor speed as the input. So I enable the curve, and then it's the speed which achieving the given discharge pressure and considering the volumetric flow rate to the compressor, the speed is found. So alternatively, in some cases, we want to find out, for example, the maximum head at the maximum speed. The maximum speed is 11,500, So I'm removing the head and adding 11,500 as the speed, and it will give me the maximum discharge pressure for this condition. Here there are many ways you can study the compressor by adjusting the speed using adjust, and also in dynamic using the like a dummy controller or a real controller, or adjusting the pressure on the discharge side or other parameters. There are many ways to study the compressor capacity, performance for your project. So this is all based on experience and exercise. This was about how to implement a curve into Aspen HYSYS, a compressor curve.